Welcome back to ECE 220. If you haven't already, I would encourage you to watch the tutorial on PSpice. The due date for that is tomorrow. Obviously, I'm not checking that, but the intent is for that to help you perform your PSpice homework, which is due in class as basically a hard copy. Make sure your name is on it, and you'll submit that to me in class on Friday of next week. Homework 2 is obviously due before that on Tuesday, and that's done through mastering, and that's then going to take you through essentially Chapter 2 material, which we've already finished. We're now in Chapter 3 material. Office hours, we're trying to get into a pattern. I have those immediately following class here if you have questions today and on Tuesday. On Monday and Wednesdays, those are at 2 o'clock in my office in room 523 of the ECE building. Tomorrow's are adjusted just for tomorrow. Normal Fridays, they will be at 11 o'clock in the office in the ECE building, but tomorrow they will be at 10 o'clock immediately following class. I'll try to get over there as quickly as possible, so they're an hour early on Friday of this week. One thing relative to the orientation lab, which is lab number 0, the TAs have informed me that you need to bring material to take notes. Essentially, they are going to be familiarizing you with the laboratory process. Wear closed-toed shoes, no sandals, or you won't be allowed into the lab. So wear something that covers your feet. That's a critical thing. Bring your CAT card, and I've tried to provide instructions for lab number 0 on the D2L course site, and you should be able to find that in the D2L or on the lab module on the content page of D2L. That just was posted, so if you were looking for it last night, it wasn't there. The instructions for lab 0 are basically show up, but make sure you have your CAT card so you can get into the lab, closed-toed shoes so they'll let you into the lab, and bring something to take notes with if they are then telling you different things about the equipment, the process, etc. in the laboratories. There is no pre-lab to be turned in for lab number 0. All of that I've tried to collect in the instructions for lab number 0. But lab number 0 also talks about the subsequent labs, which there will be a pre-lab and there will be a lab report for each of the subsequent labs. The pre-lab rubric is included in the description of the lab, each of the labs, and the lab report rubric is a separate file, and those are now collected in the lab module on the D2L course site. And a little bit of that material will be on exam number 1, which is coming up. Wow, is it 3 weeks from today? 3 weeks from today is exam number 1. In this classroom, it will be in class, and it will begin as I'm speaking now. You'll already be heavily engrossed in that exam 3 weeks from today. And that will cover, topic-wise, homeworks 1, 2, and 3, chapters 1 through 3. We're going to keep moving forward with the lectures. We'll be advancing through chapter 4 material. You won't be held accountable to that on exam number 1. And I would suggest to prepare for exam number 1, the question was, what will it look like? I'm paraphrasing. But I would suggest you look at some of the previous exams that have been administered for this class, and the link to those exams is on the course website. I would start working through those and seeing if you can come up with the answers, and it should be consistent with what we've done in class and in the homework. But it'll obviously have some variation. It's an exam. Today what I want to do is continue with our voltage divider circuits and show what we mean when they were looking at example 3.4, loading of a voltage divider. What does that mean? And then we'll look at correct and incorrect applications of the voltage divider, and then we'll get into current dividers. That's the plan. As a review, hopefully you can tell me what the formula is, or the expression for the voltage dropped across that second resistor in this two-series interconnected structure with a voltage source. Can you provide me with the expression, and I will just call this the voltage divider expression for V2 in terms of R1, R2, and V sub S. And if you can't, that's okay. You can very quickly derive it from KVL and Ohm's law. Ohm's law tells you V2 is what? I didn't know what color I was attached to. Ohm's law says V2 is R2I2, doesn't it? What's I2? Or can we find I2? Or is it related to I1? Or is it related to this I? All those I's are the same, aren't they? It's a series circuit. I is the same as I1 is the same as I2, and I you could find if you just knew the total resistance. And what's the total resistance of a series connection of two resistors? That's just the sum of those two resistors. So in fact, I is right there. V sub S divided by R1 plus R2. And Ohm's law says, oh, it's R2 times I2. Well, we just have I2 right there, so this is now R2. And here's your voltage divider expression for a two-series interconnected network of resistors. Meaning, if you didn't remember that, you now derived it very quickly. What about an N series of resistors? A series of N resistors. What's V sub 3? Do you see I'm hoping you kind of do the same strategy? The current through all of those resistors is the same. It's, let's say, is I. Can you find the current I? By Ohm's law, that would be V sub S divided by the total resistance. And the total resistance is the sum of all of those series resistors. Or the expression here, if you wanted to make it a little bit more compact, you would say, oh, the total resistance is the sum of all of those resistors. And if I divide that into V sub S, that gives me the current I. And to find R sub 3, to find V sub 3, Ohm's law says scale that by R sub 3. And if you needed now V sub L, well, maybe I should use a different subscript. V sub little n, that would just be R sub little n, and everything else would stay the same. This really should be a review. Question?
Is there another way you can draw that circuit to show that that's the sum, but also the 2 roots?
I'm not quite following the question. The question was, is there another way to redraw that circuit?
Have one variable for the sum, but also.
So you could draw it a little bit differently. I would say you might do this. But this is not quite the total impedance. This is just the sum of all of those resistors without R sub 3. If I say this is now R sub 3, this would be, we'll put a hat on it. He seems to be going to a party. So that's R equivalent hat, which is now R1, R2, no R3, R4, R5, etc. That's the R equivalent hat. And that's the picture that you could show or think of that's consistent with this one, in a sense. Did that answer your question? So this guy is now R1, R2, R4, up to R sub n. And I've skipped over R sub 3. R sub 3 is not included in the dot, dot, dot. This is still V sub s. Again, it's however you want to visualize these, whatever way sort of makes it clear to you. This is still the same current I. Let's look at that a little bit differently. Now, instead of having R equivalent hat, this parting resistor, we're going to put that into a slightly different form. Now we're going to put it into the form of a potentiometer. We now have essentially a resistor that we can now slide along to adjust the fraction of that resistance we actually see at the terminals that I'm labeling V plus and minus. The total resistance we might just say is R, and you might have a potentiometer that's 1,000 ohms. That means you have a dial on that potentiometer. That's what the picture was for. That is a physical potentiometer. You can turn the dial, or if you have a really tiny screwdriver, that gold cap on the blue box is actually an adjustment of basically a thumb wheel adjustment on the resistance in the blue potentiometer. Those might be 1,000 ohms, and you can now twist that dial to dial in a particular resistance between 0 and 1,000. And here I'm representing that dial's setting by the variable alpha. And I've sort of shown it two different ways. The right corner, don't worry about that for now. Let's focus on what we have in the leftmost panel. And do you see how the formula arises? If that knob is now adjusted an alpha an amount, and alpha is now varying between 0 and 1, now maybe we have 25% of that knob turned. Now we're going to have 250 ohms in the lower section of that potentiometer. Alpha is 0.25 in that example. That means that the R sub 2 that you're used to seeing is 0.25 R, where in this case R was 1K. The total resistance, that was the entire sum of all of those stacked resistors in series. That's now R, which in this case is 1K. And we have R sub 2, alpha R, divided by R total. Well, the R's are the same. They can cancel, and now you can see that we really just have a fraction of our total source voltage divided onto this V that we now have determined by the adjustment of the knob on our potentiometer. Another way of applying or thinking about the voltage divider circuit. If alpha is between 0 and 1 and the bottom half is alpha of that, then the other top half is 1 minus alpha. If we had 0.25 at the bottom, we have 0.75 at the top. And now you could pull off two different voltages if you wanted to, a V1 and a V2, and they are going to be dividing the total V sub S by however much you've adjusted that potentiometer's dial by alpha, the setting alpha. Have you seen these floating around? Have you ever opened something up and you've seen a little blue box? Or maybe this, in the past, a lot of your dials on different electronics might have been a potentiometer. And now they're inferring from that the setting that you want for your particular system or device that you're interacting with. Let's get back now to the cautionary tale associated with voltage dividers. Yes?
Back to the potentiometer.
Mm-hmm.
Wouldn't the total resistance of it be the same?
So the total resistance in the potentiometer is the same. That's the R. In the example I said if we had a 1,000 ohm potentiometer, that's 1,000. So that's what we were always putting, the total series resistance we were putting in the denominator. That's the R in the denominator of our formula. Is that what you were asking? So that stays fixed if you have a fixed potentiometer. And then how much of that you see at the bottom depends on how you've adjusted the dial. So alpha could be anything between 0 and 1. Some pots are a 10-turn pot, so it takes you 10 turns to get all the way through that resistor. Some are a quarter turn, some are a half turn, some are a full turn. It's however you want to buy that potentiometer or however the company designs it. Here's the cautionary tale associated with voltage dividers. You can't get locked into always assuming that when you have R1 and R2 stacked on top, that you can always just blindly apply the voltage divider to find the voltage across R2. Especially, and here's the caution, is especially when you have something else attached to the two nodes that R2 is connected to. Here, R sub L is also connected across the resistor R sub 2. And if you're asking or wanting to know what is this voltage V sub 2 in this circuit, so what is V sub 2? What you can definitely say is what it is not. It is not the standard voltage divider formula because it's not the standard configuration. We've now attached something else to or across R sub 2. And that something else here is R sub L. L is standing for load. You might now, I was going to cover this up, but that doesn't do me any good, does it? If I cover up that R sub L resistor on my tablet, you're still seeing it. All right, so virtually cover up R sub L and think of this as like a power supply. Maybe you wanted 3 volts and you had a 9-volt battery, and you picked 2 resistors in such a way that you were able to get, what did I say, 3 volts at V sub 2. And now you say, okay, I want to use that 3 volts to supply or power some device. So you connect this device up to that node, those 2 nodes across R sub 2, and you go, okay, give me 3 volts. Depending on the resistance that that load presents to your circuit, that's not going to be the 3 volts that you were expecting. You've now loaded your circuit. And that's the why. You now hopefully understand that R sub L loads R sub 2. If that's the case, how do we find V sub 2? And I'm suggesting the following analysis will work, and I'm sort of going back to an earlier question. I've now redrawn this circuit as something that we're comfortable with, that we're used to seeing, but I didn't label the bottom resistor. Is that R sub 2? I want this circuit to be the same in behavior as this circuit. If that's the case, what have I now done to that? Did we talk about this last time? Those 2 resistors are in parallel, aren't they? How do you combine parallel resistors to give you a single equivalent resistor? We could call that R equivalent and say, oh, R equivalent is the parallel combination of those 2 resistors, which was R sub 2 and R sub L, the product, divided by their sum. And if that's the case, then can you tell me what V2 is? If we've now calculated, if somebody gave us R1, R2, and R sub L, now we're in a pretty good shape to tell them what V sub 2 is going to be. What is V sub 2, the expression for V sub 2? Isn't that the voltage divider formula that we're used to, but now we need to interpret it with these labels? We're going to divide the original voltage, V sub S, in some way. What's the total resistance? Isn't it that? That's the total resistance that that source is seeing. And what resistance are we measuring across to determine V sub 2? That's just R equivalent. And that's now our standard voltage divider formula. The question is, what's always on top is R1. I'm not going to say that. Is that? Oh, so the numerator variable is, in the way that we've been structuring it, that's the resistor across whose voltage we're trying to measure or obtain. So the resistor in the numerator is that. And why is that? Because you can now find I, you could do KVL, and derive that same formula. The voltage, V sub 2, is R equivalent times I, and I is V sub S divided by R1 plus R equivalent. Does the size of R sub L matter? Meaning, if I now wanted V sub 2 to be 3 volts, yes, question.
Is the voltage through RL the same as through R2?
Is the voltage through RL? Oh, so now is the voltage across R sub L V sub 2? Is that your question? Is that the same? What voltage is R sub L seeing? R sub L is in parallel with R sub 2, and by definition of parallel, they have the same voltage, don't they? So R sub L does have the same voltage, V sub 2. It's just V sub 2 is not the traditional or the standard V sub 2 from I wanted to cover that up again. The standard voltage divider with 2 resistors. Now we have 2 resistors with a load resistor attached, and that's what messes it up. But it still sees the same voltage V sub 2, but that voltage is not this V2 in red, it's this V2 in blue. And this expression differs because our equivalent is not quite R sub L, is it? But now we're saying, how does this work? When can we sort of say, oh, maybe it's okay to use the traditional voltage divider formula? Are there values for R sub L that we could maybe say, oh, that's not really loading R sub 2 that much? So all right, is everybody ready for a little analysis? Let's work through this. Suppose now V sub 2 is what we just said it was. It's R equivalent over R1 plus R equivalent V sub S. We're trying to figure out a formula that would allow us insight into how R sub L influences this voltage V sub 2. Let's make this a little bit more messy. Let's go ahead and put in the exact formula for R equivalent, which was R2RL over R2RL, R1 plus R2RL over R2 plus RL. Now we're really getting somewhere, aren't we? Can we see? Kind of being facetious, but we can clean this up a little bit if we do the following. If that R sub 1 term in the denominator was on top of R1 or R2 plus RL, we'd have common R2 plus RL everywhere, and we could cancel them out. We can force that by multiplying by 1. Meaning, let's now rewrite V sub 2. And here's our multiplication by 1. And we now have R2RL over R2 plus R sub L. That's just 1. R2 plus R sub L over R sub 2 plus R sub L. And now, the reason I did that, you're just making it worse. Be patient, be patient. Now I can cancel that, and that. And now instead of having ratios of ratios, I now just have one ratio back. I now have R2RL over in the numerator, and I have R1 times R2 plus R1 times R sub L plus R sub 2 R sub L. Oh, come on. I thought you said you were going to help here. R sub L is sprinkled around a little bit more. Let's sprinkle it some more. If we just had an R sub L in that first term in the denominator, we could cancel all of the R sub L's, or at least one of them. So I'm going to multiply by 1 again. Meaning here, I'm going to multiply by R sub L over R sub L. That's 1. Haven't changed anything other than the ability to do some canceling. Now I can cancel that, and that. Meaning, I now have R sub 2. Well, that's looking familiar. That's our old voltage divider numerator for just R1 and R2. I then have R1 plus, well, can I add these together? There's this one. And now I'm going to combine and factor out an R1. So I now have R2 over RL. That's that piece plus R sub 2. The idea was to make this look like what we were used to seeing, which was R2 over R1 plus R2. And it almost does, except R sub L now is appearing in one additional term, and it's in the denominator. We can kind of look at different limiting values of R sub L. What if R sub L went to infinity in this formula? Let's look at some limiting cases. What's it mean for a resistor to go to infinity in this case? If R sub L goes to infinity, what does that really look like? If R sub L gets really, really big, what do you see here? If R sub L gets really, really big, what happens? Well, the opposite. What happens if it gets really, really small? That's a wire, isn't it? If it gets really, really big, what is it? It's gone. It's an open. If our resistor R sub L gets big, it's gone. It's an open circuit. If R sub L gets really small, it's a short circuit. So we're now looking, we're looking at the really, really big case. And what does this formula say? This now, I tried to convince you that now there's really no R sub L attached to the circuit. And if there's no R sub L attached to the circuit, we're back to our standard or classical voltage divider formula. And that formula actually is consistent. If we let R sub L go to infinity, that second term in parentheses vanishes, and we're back to R2 over R1 plus R2, our standard classical voltage divider formula. Meaning, as R sub L gets big and big and big relative to R sub 2, you can kind of neglect its loading influence on the rest of the circuit. That's the punchline or the bottom line. If R sub L gets really, really big relative to R sub L, and what's really, really big? It's going to depend on the situation, but it could be a factor of 10. That may not be big enough. Maybe it's a factor of 100. So if R sub L is 100 times as big as R sub 2, I'm going to neglect its influence and just do R2 over R1 plus R2, and that's V2. Do you see what I'm trying to get you to think about or understand? What about the other case? What if we let R sub L go to 0? You told me that was a wire, so now we've short-circuited R sub 2. Now it may look a little bit weird letting R sub L go to 0. Now we have infinity in the bottom. Let's go back to an earlier formula and say what happens when R sub L goes to 0 in R equivalent. What's R equivalent become when R sub L goes to 0? Doesn't it go to 0? Now what's V sub 2? 0 over R1 plus 0. 0 times V sub S, 0. So V sub 2 becomes 0 when you short out R sub 2. And those are checks on the behavior of that loaded classical voltage divider circuit, where you're now varying the load R sub L from 0, a short, all the way up to nothing where it's disconnected. Let's look at some examples of correct and incorrect. Now we've seen both. We've seen the impact of loading a classical voltage divider circuit. Here's now a new circuit, and we want to start analyzing it. And I think you know my next question. Is V sub 2 equal to R2 over R1 plus R2? This is now a slightly different sketch, but it's similar to what we just talked about. It's very similar to example 3.4, is it not? What's R sub L in this case? Do you see it? Do you see R sub L? Or is it hiding? It's hiding in plain sight. What is R sub L in this circuit? And now you need to kind of get used to putting on your augmented reality glasses and seeing this circuit morph into what it was before. Meaning lengthen that line above V sub S and bend R1 vertical, and then squeeze R3 and R4 into something that's vertical. Now do you see R sub L is actually R3 plus R4? That's now loading R sub 2, so V sub 2 is not this formula. Even though you want to apply it maybe, this is a big no. Well, R1 and R2, aren't they in series? Yes. Yes, so R1 and R2 are not in series, are they? Because their R2 is being influenced by what's to the right of it, which is this loading effect of R3 and R4. R1 and R2 are not in series. R3 and R4 load R sub 2. Now, is there a voltage divider hiding in this circuit? Can we find a voltage divider, or why did you spend so much time talking about the voltage divider and now you're telling us we can never use it? What kind of instruction is this? So is there a voltage divider hiding in that circuit anywhere? Can you find a voltage divider or the application of a voltage divider? Look to the right. Look to the right. V4. Is V4, can we find that via a voltage divider? What is V4? Do you see if we knew V sub 2, we could divide it among R3 and R4, so we could find V sub 4 if we knew V2. That's the big if. If we knew V2, we could find V4 by a voltage divider. Oh boy, I keep losing. Sorry to dirty up your paper with those scribbles, but that's the only way I can space my stuff. I thought I captured them all before. Maybe I'm on the wrong page. Is there a voltage divider in the above circuit? Yes, and it's this one. And what would V sub 4 be? What's a formula for V sub 4 in terms of V sub 2? If I'm answering yes to that circuit, and if V sub 2 is across those left terminals, what's V sub 4? What's in the denominator? What's the total impedance if V sub 2 is sitting there? And what are we measuring, or what's Ohm's law? It's R4 times that current through R4. However, the big however, we must find V sub 2 first before we actually find V sub 4. How do we find V sub 2?
Are we allowed in calculating, if we're just looking at the left-hand loop, to kind of neglect R3, R4, and V4, or trying to find V2, or is that not?
So now the question I think that I'm hearing, I'm sure everyone heard that. You have much better hearing than I do. Did you hear the question? Oh, good. I'll try to repeat it. Can we just neglect R3 and R4 to find V2 in this circuit? If we want to find V2. No, we can't just throw them away and then put them back. So we have to keep them present. Was that your question? So we can't virtually erase R3 and R4 and say, well, I can find V2. That's the voltage divider. Yeah, it is, but you now have to treat it differently. What do we have to do? We have to load R2 and give that an equivalent resistor, and then find V2 from that.
Do you normally just go into the farmost right until?
The question was, do we always go to the far right and then work from the far right back to the left? The way we cook up the circuits in this class, a lot of times, yes. But in reality, you may have loads on the left, loads in the middle. You may have to re-sketch your circuit in order to make it look consistent with what we're doing here. But the strategy is, for first exposure purposes, it's helpful to kind of view it all the same all the time. So now we're sort of working, collapsing things from the right to get to our source, and then we can solve from that. In this case, what do we want? Well, now we want to find V sub 2. And the way that we're going to do that is how? Now we can say, well, here's the source. Here is R1. And here is another resistor, and what's that resistor look like? Well, that's now R2 in parallel with the sum of R3 and R4. Is that notation okay? We're adding R3 and R4, that's R sub L, and we knew from before that what we need to resistor-wise to have to measure V2 is R equivalent, which was R2 in parallel with R sub L. So if we now call this R5, if we had numbers, we could calculate R5. If we had numerical values for all those resistors, then what's V2? If now all of that mess in the cloud, everything's in the cloud these days, so I just went ahead and put these resistors in the cloud. If you have your Google account, you can find it, right? On an exam, you won't be able to do that. Your cloud's just going to be this area above your head floating around, but hopefully you'll have all sorts of ideas floating around there. It's Thursday. One more day and the week will be finished, right? R5. How do we use R5 to find V2? Isn't this our classical formula? R5 over R1 plus R5 V sub S. And now we can apply this we can now use that V2 in the V4 expression that we had before. But V2 now is different, isn't it, than the classical V2. What if I now gave you this circuit? This we'll call a bridge circuit. R5 is sort of bridging between two nodes. Can we simplify that network of resistors using our series parallel combination of resistors? How can I simplify that connection, that interconnection of R1, R2, R3, R4, and R5? Do I have any series connections? Do I have any parallel connections? Are R1 and R3 in parallel? What do we think? Is R1 and R3 in parallel? Do they share two nodes that they are both across? Unfortunately, that bridge is in between them, isn't it? R5 is separating them, so there's three nodes connecting R1, R3, and R5. What about the bottom? It looks the same. It's just upside down, isn't it? Do we have anything in series? If R5 was gone, we would, wouldn't we? If R5 went where? If R5 became 0 or infinite, what do we need R5 to become for it to disappear? Do we want R5 to be a short? No. We need it to open circuit. We need it to go to infinity. We need it to disappear so we can erase it. Then R1 and R2 would be in series. R3 and R4 would be in series. And those two branches would be in parallel. That bridge is causing issues, isn't it? That bridge has caused nothing to be in series or in parallel in this configuration. We have no series or parallel connections. We need another approach. And if you're paying attention to me physically, you know I'm not looking up intentionally, so I don't see a timeout given. Here are some observations, just to be thinking. Now I want you to start seeing triangles and Y's, or pi's and t's. Do you see a triangle in that? If you looked at just the top, R1, R3, and R5 would form a triangle. If you looked at just the bottom, you would have another triangle. And if you spread out the node between bottom of R2 and R4, do you see kind of you have a pie shape? We get very creative with our shapes. But a triangle or a pie, you can sort of think of similarly. And then finally, I will stop. Do you see that you could also look at these as like a Y on its side, either going to the left or to the right? And if you bent those branches a little bit, flattened them out, or made them more vertical, you would now have a T on its side. So now the Y's could be called T's. So you have pi's and t's, or deltas and y's. We have to figure out how to convert between deltas and y's and deltas in order to simplify these bridge circuits. We'll pick up at that point. Thanks for your patience.